have tried to.
You should put your songs on
It makes me really curious. I've done a lot of research on brain and stuff like that, but just kind of what all happens at night when it's all wide down. So that really, that factor of stuff, because it really makes a difference.
You're saying earlier about how you're
Right, morning everybody. Go ahead and get started. So today we're going to keep talking about graphs. We're going to talk a little bit more about path searching algorithms. So yesterday we talked about DFS, and BFS. Today we're going to talk about Dijkstra, which I think you all have maybe seen at least a little bit, but it's a fantastic algorithm, so worth reviewing. And then we'll talk about A*, which is something I don't think you've seen before, and is a minor tweak on Dijkstra's algorithm that makes a huge difference. So, and then we'll talk a little bit more about different visualization techniques. So if we're going to draw a graph, what are some of the options that are disposable? So, talked about DFS. What's the data structure that we use with DFS? DFS is the stack algorithm. BFS is the queue algorithm. Dijkstra. What other data structures do we have left? Tree, yeah. So it's actually a priority queue. So these all work very similar. Basically, we store the nodes that we need to explore in one of these data structures, and the particular data structure we pick determines the behavior of the algorithm. So the BFS and Dijkstra are both use queue-based data structures. Dijkstra uses a priority queue, and specifically one that's keyed on distance from the source. When we don't have weights on our edges, BFS actually does exactly this, right? If we just search through our graph in BFS order, we are going in the same order as if we built a priority queue keyed on the distance, right? Because we're looking at things that are one edge away first, and then 2 edges away, and 3 edges away. So it happens that when we have a graph without weighted edges, these two things are exactly the same. But if we have weighted edges, then BFS doesn't really do what we want, right? We're looking at the number of edges that we'd have to cross along the path, but we saw yesterday that that doesn't necessarily correspond to the cheapest path, or shortest if your weights are like time it takes to travel between 2 nodes or something. Okay. So we'll look at Dijkstra's algorithm. Say, okay, what do we do when we have weighted edges in our graph? So Dijkstra's algorithm is named after Dijkstra, not because it is some complicated, brilliant algorithm that he spent a decade coming on. It's named after him because he was basically the first person to recognize the problem, and this is the most obvious, simple solution to this problem. And if you identify a problem first, you get to name stuff after it. So, had any of you, recognized this problem, spent a week or two thinking about okay, how would I do this? The obvious, straightforward solution that you come up with is Dijkstra's algorithm. And he was just lucky enough to be the first to come up with this. So, yeah, let's talk about the algorithm. So we have a weighted graph. And then we have a source and a target that we're going to search for. And so as we go through this, we're going to keep track of two things for each node. One is our best estimate of the distance to that node from the source, okay? And the other is what is the previous node along that path. Okay? And that's so if we have the previous for each node along the path, then we can reconstruct the whole path to the end by just kind of going backwards. So if we only care about the distance, we don't need to think about what the previous was. But if we want the path, then we have to. Okay. So I have my source and my target. Okay. To start with, what's my estimated distance to every node going to be? Infinite. I don't know. I don't even know if I can get there. Right? I haven't looked at any edges. Right, so for all of my nodes, is that green marker behind you work? So all of my nodes are infinite away. Okay. And if the distance is infinity, then there's no previous node, so don't have to worry about that. Okay. And then I have one node that I know the distance to exactly, which is the source, right? So the source, I know the distance is 0. Okay. So this is how I set stuff up. Cool. Right. And so what I do is I just store the nodes that I need to explore in a priority queue keyed on this estimated distance. Okay. And when I explore a node, I pop it off, I look at all of its neighbors, and I perform some updates and add them to the queue if necessary. Okay. So to start with, right, maybe I should label these. So I have A, B, and C there. So to start with, my queue has source of distance 0 in it, and that's all. Okay. And so I'm going to pop that off and explore it. Okay. And so to explore it, I'm going to look at all of the neighbors. Okay. For each neighbor, I'm going to see, could I get to that node faster through the node I'm looking at than I have seen so far. Okay, so if I have already seen a path there, is a path that goes through me going to be better? Okay. So what would the cost be of a path through me to another node? So the weight of the edge from me to that node plus the length of the path from the start to me. And so that's what I look at. I say, okay, what's if the path went through me, what is the cost? If that is an improvement over what I've seen so far, then we'll update it. Okay. So don't think I picked very interesting numbers, but we'll see. So I'm looking at S, okay? And so for each of the nodes that S touches, I can look at the cost estimates and see if I have an improvement. So the cost to S is 0. So the cost through S to any of these other ones is just going to be the edge length. Okay? So for this one, if I go through S, the cost would be 4, which is better than infinity. Say okay. This one, 5, better than infinity. 3, better than infinity. Okay. And then I go ahead and I add these to my priority queue. So now I have I'm actually going so now I'm going to have A, 4, B, 5, C, 3 in here. Right. Now I'm done looking at A. Oh, also when I update these, I'm going to update the my previous. So if I changed my estimate distance, I have to say, okay, to get there, you have to go through S. So all these. So for all 3 of these nodes, I found a better path to them, which is kind of silly in this case because there was no path before, but now there's a better path. Okay. Cool. So I just keep going through this. The next, my priority queue is going to, when I pop from my priority queue, I'm going to get C. Right? So my next node I'm looking at is C. For C, I'm going to look at all my neighbors. Okay. So from here, so I'm going to look at S, B, and T. Okay. For S, what would the distance to, or what would the length of the path to S through C be? It would be 3 for, it takes me 3 to get to C, and then another 3 to get to S. So path cost of 6, which is not better than 0, right? So I leave that one alone. It's not updated. To B, the path cost through C would be 5, right? Which is the same. I'm going to tweak this to make things a little bit more interesting. Now the path cost is 4, right? Things are better. All right, so now let's change this. It's going to be a 4, and instead of going through S, I'm going to go through C. Okay. And for T over here, 6 is better than infinity. There we go. Okay. And so for the ones I've changed, I'm going to put them in my priority queue. So I have T, 6, and B, which is now at 4. So if depending on the type of priority queue I use, I might be able to just update the weight here, or I might have to do like a search and remove, or I could just insert the duplicate, because I'm going to pick this one before I pick that one, and doing this one, I'm not going to change anything. So depending on exactly how you store your priority queue, you may or may not have duplicates. Good. So our next node we'll look at, let's say we look at A next. Over A, we look at B. Going through A would cost us 6, which is worse than 4. Ignore it. Going to T would cost us 10, which is worse than 6, so we ignore it. Going to S worse than 0, ignore it. Right? So we make no updates here. And then we get to B. When we get to B, we look at C and A. Okay. These aren't going to change. But T, we actually can improve on a little bit. Our 4 plus 1 is less than 6. And we can stick our T5 in here. Okay. And so this doesn't do anything. And when we pull out our T of our Q, it actually doesn't matter how much stuff is still in our queue. At this point, we know we're finished. Anybody have intuition for why that is? Yeah, so the queue in here, right, all the things are the shortest path to a node, right? So the path to T through anything left in here is going to be longer because it takes longer to get there, and then we have to go even further to get to T. So there's no way that anything that's left over in here can give us a shorter path to T. So yeah, the way we explore with Dijkstra's algorithm is we explore the closest nodes first. And as soon as we're ready to explore the target, we know we found the shortest path. Okay. So that's Dijkstra's algorithm. Again, it's kind of like, you know, if you sat and stared at this for a while, it's kind of what you'd think you'd do. Say, okay, well, just keep track of how long so far, and then update things if I have to. Okay. So let's go ahead and we'll write out the pseudocode for this. So we need a PQ to start with. We need a, so yeah, this is a priority queue. We need a our distance estimate. So one way we store this is just as a hash table. So map from node to estimated distance. And then the previous, which also could be a hash map. So we map from the node to the one before it. And then to start it all off, right, we just stick the first node in into our priority queue. Right, so PQ insert. Source is at 0, the distance estimate, the source equals 0, and we'll ignore the previous for the source. The nice thing about using hash maps for all these things is basically we don't have to initialize everything to infinity. So how do we tell that the distance is infinite? Yeah, if it's not in there, then it's infinite. So it's going to save us some space and some initialization time. Okay. So we start here, and then we just go while the PQ is not empty. We'll start by popping our node out. And then we look at each neighbor. So for each neighbor in here, right, the updated cost, right, or the proposed cost is the distance to n plus the edge length from n to I. move on up here. All right, so we have this new proposed cost. What do we do with it? So this is how long it would take to get to I if we went through N. Is that the path we should take? Maybe. Compared against what? Yeah, so if the proposed cost is less than our estimate, then we have found something better and we should update it. So then we should do the estimate is the proposed cost. The previous for I is now N. Right, so the best way through here is through N. And then now we have to make sure we look at I to find its neighbors. Right, so we want to add it to the priority queue. Good. We can add a quick exit. So here, right, so I might add in here if n equals t, or return the path. So we'd have to actually build up the path based on our previous table, but that's pretty straightforward. Yeah. So let's Dijkstra's algorithm. Yeah, it works. It's kind of the best you can do for this type of thing, where we just we just expand out. We look at all the nodes kind of in closeness order to the source. Any questions about Dijkstra's algorithm? So Dijkstra's algorithm suffers from the same issue as breadth first search, which is that if you kind of look at it happening, it looks kind of like a bomb going off. It just goes out from the source until it hits the target, right? Which seems kind of dumb, right? Because the target is in one direction, right? And we're growing out in every direction, right? Seems like we should make use of what we know about where the target is. And so that's where A-star search comes in. Okay? A-star search is almost exactly the same as Dijkstra's algorithm, except that we add a little bit of extra knowledge that we can use when we search. Okay? And for A-star, we add what's called a heuristic function. Okay. And this is a function that takes two nodes in our graph and estimates and returns an estimate of the distance between them. And as long as we can get a reasonably good estimate efficiently, this can actually help our search a lot. Okay? Let's say we're doing like directions in like for Google Maps. Okay. We somehow need to estimate the distance from, between two intersections. Okay. We don't really want to compute the whole path there because we're, that's that's not really making our problem any easier. Like we're finding a path, so if we need to find paths to find a path, that doesn't really help us out. But if we just want a quick estimate of the distance between two things, what can we do? You just look at the Euclidean distance. Okay? Say, okay, well, from here to here is 1 mile. Okay? You can't drive that, right? You're going to go through somebody's house, but that's like a quick estimate, right? If things are further apart in terms of the path that you have to take, they're going to have a longer estimated distance, right? Things that are closer in terms of the real path, they're probably going to have closer estimated distance, right? And so we can use this information to help us, right? So even if my estimate isn't quite right, it still tells me if I'm going in the right direction. And so that's the idea. So with A*, we use this heuristic function to help guide our search. And so basically the only change that we have to do here is we change our priority queue. And instead of being keyed, for Dijkstra's algorithm, our priority queue is keyed on the distance from the source, right? What we're going to key on in A* is the estimated distance from the source to the target. Right? So this is made up of 2 pieces. The first part is if we already know how to get from the source to this node, we have the exact answer. So we know that part exactly, right? So we start by using the distance estimate. So we'll say estimated distance from source to the target through a particular node n. Right, so we start by using the estimated distance to n, so how to get from the source to n, and that we know this exactly because we've been expanding out from the source. So this is exact, okay? And then to go the rest of the way, we use our heuristic function, and that's going to estimate the rest of the way. Okay. And so we key our priority queue based on this new thing, right? And this is going to cause us to explore things that are moving in the right direction before we explore things that are going the wrong way. Okay. So this is the key bit, is we include this estimate in our priority queue keying, right? And this is going to do a better job of ordering the nodes for us. Who thinks that this is going to still give us the shortest path? Right, we're including some estimate in here, right? So we're kind of guessing, right? So you could imagine, like, maybe if you have a bad guess, you actually miss the shortest path because your guess kind of leads you in another direction. So actually, we have to be careful about this function h that we use, or we might get the wrong answer. And it turns out that as long as there's a few different ways of defining, an appropriate h, but basically, as long as h is an underestimate of the true distance, then this is going to give us the optimal path. Okay. When we're doing, like planning with the car, and we pick the as the crow flies distance, the straight line distance between 2 points, that is going to underestimate how far we'd have to drive to get between them, right? So that is an acceptable heuristic, and if we use that, we will get the same shortest path at the end from A star that we would get from Dijkstra. Yeah.
Do you run into any issues where, like, so with the car example, where maybe you're heading north, you have to go back, backwards like 2 streets, and then over, and then that's longer?
So we'll look at an example where that happens. Basically, the heuristic usually doesn't know about like obstacles, right? It assumes you could just go in a straight line. So what A star will do is it'll steer you right into where the straight line is, and then you'll have to kind of backtrack around that. But you'll get the optimal path at the end, as long as your graph and your heuristic play by the rules. Let's say you're a helicopter pilot trying to do this path planning for an inexplicable reason, right? A helicopter can fly wherever. You try to use as your heuristic the Manhattan distance, where you go along the blocks, right? Is that going to work? No, because you can actually, your actual path will be shorter than the heuristic that you measure, so that's not going to work. Okay. So, yeah, that's the rules for your heuristic is it has to underestimate the cost. So the name A star comes from the fact that this is an optimal algorithm, and there's a proof that says basically all of the nodes that you look at when you're doing A star, if you were to ignore any of them, if you were to skip looking at any of them, it's possible that you would miss the shortest path. So to be sure, to be absolutely certain that you find the shortest path, you absolutely must look at every single node that A star looks at, right? So A star is the best algorithm you could do for finding shortest paths. So, yeah, very small tweak, right? We just are changing what we're keying our priority queue on, but this adds a lot more information and it can steer us directly to where we want to go. Cool. So yeah, any other questions about this graph search stuff? So there are, this is a field that, I don't know, you might think is kind of finished and there's not much else to do there. Right? But actually there's like a bunch of research that still goes on in path planning and graph search stuff. I had a colleague at University of Denver that works on this stuff, and a couple of years ago he solved like a 50-year unsolved problem about basically what happens if you try to do A star from both ends. And it seems like it would be a good idea. In practice it doesn't work very well. And they came up with like a nice proof about what's going on. So this is still a very active area of research, even though it seems pretty straightforward and simple. Cool. All right. So for the rest of the day, we're going to talk about graph visualization. Okay. We talked about some of the analysis stuff we can do, but if we just want to look at things visually or we want to explore them, what are our options? So if I asked you to draw a graph for me, what's kind of the first thing that people would do? They're like, okay, what would your picture look like? It probably look like that, right? And that's kind of the most fundamental or most common graph visualization technique. That's called a node link diagram. So for these, we have some sort of mark for the nodes, right? So they might be circles, they might be something more complicated if we're trying to include information about the node attributes, right? But our nodes are some sort of mark. And then our edges are some sort of line or curve that connect them. So these are kind of the most straightforward way that you would think about drawing a graph. Right? We're literally drawing the nodes and edges, which is how we define graphs. So is this always a good representation, and what are some of the issues that come up with it? That's what we're going to talk about now. So when we're doing graph visualization, we're not doing it to draw pretty pictures. Right? We're doing it to accomplish some sort of goal, right? And usually that is either conveying some sort of information to whoever's looking at it, or allowing us to interact with and analyze our data in some way. Right? So we're not. So when we're thinking about these visualizations, right, we always need to have some idea of what goal we're trying to accomplish when we do this. Okay. So there's a few different types of goals that we might look at. So we'll start by splitting into two. We have the attribute-based or the topology-based. Okay. And this depends basically, are we interested in information about particular nodes? Or are we interested in information about the connection between nodes? Okay. And so the attribute-based tasks, we're looking at, if the nodes have some data associated with them, right, we're interested in that data. And the way things are connected is important, but we're generally interested in those attributes, not necessarily like just the graph structure. Whereas for topology-based, we're interested in how things are connected in the graph more than we're interested in particular data values at nodes. Of course, we could be interested in both. Right, so we'll talk about what happens when we have sort of hybrid challenges, but these are kind of a way of splitting our goals in half. So within these, we'll talk about a few different types of goals we might want to do. So we might want to localize, maybe search. We might want to quantify, say count, or sort, or order. Okay. And within these, we could have attribute-based or topology-based goals within any of these. Okay. So for localize, if we're interested with attribute-based things, right? We're searching. We want to find something based on attributes. So an example is we might want to find the edge that has the maximum weight in the graph. Right, so we're trying to find something, and it's dependent on an attribute of in this case, an edge. Okay. Topology localization might be looking at all of the neighbors of a particular node. Right. So again, that doesn't necessarily depend on the weights of the edges. It depends on the fact that there are edges there. Right? So localizing, we're trying to hone in on a very small area of the graph and look at what's there. For quantifying, we might have an account. So attributes-based stuff, we might want to count the number of nodes or look at the average value of a particular attribute across nodes. For a topology-based task, we might be looking at the degrees of nodes. Right? That depends on the connectedness of the graph. For sorting, for attribute-based, we might look at sorting by edge weight. And, for topology, we might look at paths or searching outward from a node. And so depending on what particular tasks are going to be necessary for our analysis, right? The choice of visualization that we use might be different. So we'll start with the node link diagrams and kind of see what they're good for and what the challenges are with working for them. So the major challenge for working with node link diagrams is where do you put the nodes? And where in the picture should you put your nodes? Okay. So any thoughts on good or bad ways we could determine whether we have good or bad node placement? Yeah, so we would love to minimize edge crossings. That makes it harder for us to understand what's going on. What else? Yeah, we want to not have the nodes overlap. So we don't want nodes on top of each other. What else? Let's say this is an unweighted graph. Is this a good representation? What's wrong with this one? Yeah. So ideally, we'd like to have, for an unweighted graph, have similar edge lengths. If there's weighting, then maybe we'd want them to have some relative edge length. I'll just write down similar edge lengths. Okay. About that. It's weird. What's weird about it?
There's
a single curved line.
Yeah.
It's not as pretty.
Yeah. So in general, curves are going to be harder to follow than straight lines. So we'd like to keep our edges as straight as possible. All right. What's wrong with this one? Again, assume this is an unweighted thing. Yeah, and it's not even quite so much that they're disproportionate. We have two areas of the graph that are basically the same. This is a bad picture. If I have similar structures in my graph, maybe let me try it. Does that make it a little more clear?
That you'd like it to look the same if there's so much.
I have two of the same structure in my graph, and they look totally different. Right, so I would like similar structures to look the same. Right. What's wrong there? I could make this arbitrarily bad if I wanted. Okay, where would be a better spot for this point to go? Here, right? So I would like the angle between my edges to be as large as possible. Yeah, so these are some properties I'd like. In terms of computing this, just what are some properties I'd like? What property do we always want when we compute stuff?
Like efficiency.
We want it to be fast, right? Another property that you might not think about, if I take the same graph and visualize it twice, it would be really nice if I got the same answer both times, or if I added one node, if like I didn't get something completely different. Okay. Turns out that both of those are kind of hard to do. All right, so these are some of the properties we'd like for a good node length diagram. Okay. And placing our nodes to do these things is really hard. Right? These are competing goals, right? Particular like edge lengths and edge crossings are in conflict, right? Making similar structures look the same, generally hard, right? So yeah, these are, we're not going to be able to satisfy all these.
What's the logic behind not wanting similar looking structures?
We do want similar structures to look the same. So this, here we have like a 4 connected thing, here we have a 4 connected thing. Mm-hmm. I would like them to look the same. So if I'm looking at the graph, I can spot like, oh, these two things are the same topology.
Okay, so you would want
yes,
similar connectivity and with similar kind of
yeah, you do want them to look the same. Yeah. So yeah, so these are what we would like. Any thoughts about how we actually achieve any of these things? Yeah, I mean that's kind of an answer, but we'll see that even that doesn't work that well. So one thing we can do is remove freedom from ourselves, and then we can say, oh, it's not my fault. Right? So we can limit ourselves with where we put our nodes, right? And then we can kind of punt on a bunch of these things. Right? So can anybody think of example of graphs where we have very limited or no flexibility about where we would put the nodes? Yeah, so trees we'll talk about a special case because they tend to be pretty easy actually. But even within a tree we can decide you know, how we can control a little bit of layout stuff. And what kind of graphs do we have no, you know, it doesn't really make sense to move the nodes around.
Nodes are connected and closed.
So yeah, so if we have some sort of structure to how the nodes should be laid out, so yeah, maybe they're like laid out on some sort of grid. What other situations might we not have control over the layout? I'm sure you've all seen this graph in the back of a seat back pocket. And maybe toward the back of your Hemispheres magazine or your Delta whatever magazine. There's a graph that you've all looked at where they have no control over where to put the nodes. A map, right? Why? What's special about a map that means they have to punt on all this stuff? Yeah, the position, the nodes have a position associated with them, right? And so that's not a free parameter that we can go crazy with, right? So if our nodes are fixed, then we can deal with edges, right? For the flight one, depending on what you want to do, you might not even have, not have freedom there, right? If you're trying to accurately depict the path the planes take, then you know even the edges you're not going to be able to move, but you probably have a little bit more artistic freedom with the edges. So another thing, another approach related to Jeremy's suggestion is you fix the layout of your points to add some pattern or structure to them. And a common example of that is laying out points around a circle. So you've probably all seen graphs where you have your points on the edges of the circle and all the edges are on the inside. Okay. So that's another approach is to kind of restrict your layout to make it easier to pick the best one. Okay. If we want to go totally flexible, probably the most common layout technique, which has some pros and cons, are called force-directed layouts. The idea there is we pretend that all of our nodes are little positively charged particles. Right. And if I left these to their own devices, what would happen? They would all shoot out to infinity to get away from each other. Right. And what do we suppose is keeping them together? We have edges between some of them, and what physical tool would look like an edge? Nuclear force, yeah. Maybe think physics 1. It was like one force you ever looked at in physics 1. Gravity and springs. Yeah, we use gravity that still shoot off to infinity because gravity is like way orders of magnitude, a bunch of orders of magnitude weaker than the electrical force. So we connect these with springs, and these are actually kind of weird springs. Their rest length is 0. So the springs actually want the points to be literally on top of each other, but the repulsion is keeping them apart. Okay. And so yeah, what we do, we hook up springs, and then we just run a basic, really coarse, crappy physics simulator. We don't really want realistic physics here. We want nice, controlled, damped motion. And so we just let physics happen and move these around. And that gives us a layout with some pretty nice properties. So one nice thing it does is clusters, where there's a few particles with a bunch of springs. They get pulled together, right? So we actually get pretty good clustering behavior. Okay. Things kind of spread out, so we don't have a whole bunch of stuff on top of each other usually. Okay. So these are reasonably good layouts. Edge lengths tend to be kind of uniform, just because the forces kind of balance out. So that's cool. But there's a bunch of drawbacks. So the first is that the final position of these things depends on the starting position of them, right? And that in a non-obvious way, right? You tweak the initial conditions a little bit, you could get a totally different outcome. Okay? So in general, these are not deterministic, right? Because you start with random positions or whatever. So yeah, usually if you lay out the same graph twice with the force-directed layout, you get two totally different visualizations. And so if you're trying to, look at a series of these visualizations, you can't remember like, oh, hey, there's this cluster in the right corner, because the next time you do it, it's going to be somewhere else. Yeah.
You like arbitrarily or randomly fix some of the points. Would that increase the likelihood of you getting similar looking?
Yeah, if you added some constraints, that would help. Yeah.
If you just said like this point always is here, for instance, that maps around that.
I think you'd need to fix a few more, but yeah. So that's going to introduce some bias into how things are laid out, but it would increase determinism, so trade-off. Yeah, another downside is it's pretty slow. So there's repulsive forces between all of these. Right, so if you're naive about doing this, it's basically n squared to compute all the forces. It takes about n steps of physics to get things to calm down in general. So this is potentially an n cubed kind of thing, which is pretty bad. You can be smarter about how you compute forces and cut that down, but still not super fast. Another issue is it generally never comes to a total equilibrium. Things are always kind of bounced around a little bit. So you either have to, as the user, you have to deal with things that continually move, or you have to stop it after a certain amount of time or something. So yeah, for an interactive graph, you can handle about 1,000 nodes doing this, yeah, it's kind of slow. It has some drawbacks. So this is kind of the go-to for free node position graph layout. Node link diagrams generally, no matter how you lay them out, suffer from the hairball problem, where as you add nodes and edges, you very quickly get an image that's just a hairball. Like you can't make sense of what's there. There's too much clutter, too many lines to understand it. Okay. A couple things we can do to combat that. One is edge bundling. So we have a bunch of edges that are going to similar places. We can group them into a super edge and then split them out. Okay. And that can make it much easier to see what's going on. Another thing we can do is do some sort of hierarchical visualization. So grouping clusters into a single node to cut down on the number of edges we have to draw. So that's kind of another approach we can take. If we're dealing with trees, we can do some pretty cool stuff with node link diagrams. So because trees have a nice structure, we can kind of come up with a good layout ahead of time, right? So you can imagine like a table of contents is a tree. We have a very nice layout for that with like indentation and stuff like that. but there's a whole bunch of different ways we can visualize trees that we're not going to have any edge crossings. Right? The nice thing about trees is we can easily draw them with no edge crossings, right? And we have just a lot of flexibility in how we draw trees. So in general, the node link diagrams, they're like straightforward. They're good for doing local topology stuff, right? If I zoom in on an area of the graph, I can see what's there. I can follow edges, all that sort of stuff. But picking a good layout is really hard. It could be slow, and in general, it's like impossible to do a really good job. And we have the hairball problem. Cool. So any questions about node link diagrams? Okay. So the next group of representations we'll talk about are the matrix representations. And the idea here is that we're actually just going to draw the adjacency matrix. Okay, so we talked about yesterday. Right, the adjacency matrix just says it just says which edges exist. And so usually this is like a grid, and we just color code the blocks that correspond with edges, and we can use channels of our color to describe the weight of an edge, stuff like that if we want. But yeah, these are general kind of just pixel pictures. Any idea what these are good for?
Showing airline routes.
The matrix one? Yeah. So for that one, yeah, we're looking at what's special about what like airline routes that makes them better than like driving routes.
They're off one way.
One way, so directed graph stuff. Yeah, so but we don't necessarily have to follow the roads. If we drew a graph, you could say, hey, we can get from Salt Lake to Provo or whatever. How many hops do you usually take on an airline flight? Ideally one, right? And probably no more than 3 or 4, like even if you're going somewhere really far away, right? So the matrices are pretty good if you're only looking at like one row or column at a time. Right? So if we're doing neighborhood-based stuff, they can be really great. If you're doing if you're doing path planning with a bunch of hops, these can be really bad because if you look at the edges you take along a path and like color them in the matrix, they're usually not touching each other or even that close. Right? So paths through a graph in this matrix representation look like just scattershot, like unconnected, random kind of points. Right? So they're not great for path-based stuff, but they are really good for just neighborhood kind of stuff. Another thing the matrix representations are really good at is for finding clusters or cliques. So what would a cluster or a clique look like in a matrix? Yeah, so it would look something like it's going to be just like a block where everything's all filled in. There's connections between everything. So matrix representations can be really good for showing these on one condition, which is that the order of the rows and columns is well chosen. Okay? So this pattern will only show up if I have ordered the rows and columns of the things in the clique to be next to each other. Right? If I didn't do that, then I'm not at all going to be able to see this, right? It's going to be scattered all over the matrix, and I'm going to have I'm not going to be able to see those at all. Okay? So the big issue with the matrix representations is the order is really important if we want to actually be able to see these things. So there's algorithms for kind of trying to pick a good order. But again, this is one of those problems that's like, there's not a perfect solution. So those are the matrix representations. They're great for some stuff. They're not quite as general as the node link diagrams, but they're way more scalable, right? You could have like way more nodes and edges without nearly as much noise in a matrix diagram. And the node placement problem is a 1D problem, right? You're just figuring out, okay, how do I sort these rows as opposed to how do I position all this stuff in 2D. All right. The last technique we'll talk about is an implicit representation, and this is really only suited for trees. Okay? And so the idea here is instead of drawing edges between things, we are going to imply the edges by how we lay stuff out. Okay? And for trees, perhaps the easiest thing we can do is use containment. Okay? So the idea here is basically if one node is a child of another, we draw its representation inside of its parent. How many of you have used a tool called Grand Perspective? So it's a tool for visualizing disk space usage on your Mac, and it has for each file it has a little box, and the boxes are scaled relative to the file size, and everything is nested so that you can see the folder that contains the file, which folder contains that, and so there's this containment so you can see the tree structure of all your files. There's other visualizations. Anytime you have this tree structure, containment can be a really good way of visualizing it. Because we're not drawing any edges at all, right? There's way less clutter, and we can draw much larger graphs or much larger trees. The last thing I'll talk about is what if we have multiple tasks where we're interested in both topology and attributes. So let's say we're interested in paths through a graph. Is that a topological or an attribute task? Topological, right? What connections, what edges do we go through? But we might be interested in the attributes of the nodes or edges along that path, right? So we might be interested, okay, how are these nodes connected? Do they share similar features of some sort? So I guess I'm not a biologist, but apparently these types of problems come up a lot in biology, where we're talking about like genes and connections between. Can a biologist? Does any biologist know like examples of when we might have these challenges? Yeah. I assume I'm going to take it on the word of some of the researchers that work on this, that this is a legitimate problem that people have a lot. But in any case, we're mixing attribute and topology-based tasks. We have paths, and we want to understand attributes along them. Okay. So one thing we could do is like draw the attributes in like a node link diagram. So like maybe instead of my nodes being circles, each node is like a histogram or like a line chart or something, and maybe my edges have, some graph on them or something like that. Is that going to be an effective visualization tool? What would go wrong there? It's probably going to be extremely busy, right? Have just way too much information. Also, it's really hard to compare stuff, right? If I have two graphs that are like different locations of the image, maybe scaled differently, how am I supposed to compare them? Right? So displaying all this stuff in a single visualization is probably not going to work. Right? So depending on the specifics of the task, we need some way of showing both of these things at the same time. We'll look at a couple of examples of kind of research tools that people put together where they have different views of the data. So they have kind of a path. They have like a node link kind of view where you can select paths, and then once you have a path, you can look at the attributes of the things along the path, and you can kind of explore that way. So kind of a mixed mode thing for displaying the attributes. Okay. All right. So with that, I guess we'll look at a few examples. So, just look at, the slide deck is way big and most of, I would refer to the notes more than this, but there's some good pictures in here. Yeah, so this is an example of the hairball problem on a restricted layout. So this is only like 6% of all of the edges, and there's, you can't see anything. If we do edge bundling, then you can kind of see, okay, oh, there's connections between this part and this part. So, the edge bundling could be a good solution to the hairball problem. If we have fixed layouts, right, then we can't move the nodes around, but the edge bundling can help us out there as well. Here's an example of a couple of tree visualizations. Again, the regular structure of the tree makes it a lot easier for us to pick good layouts. The circular ones are kind of give you a sense for like the different levels. And this is a little bit more compact than this one. So this is an example of how the matrix representation can help you find clusters and cliques. So a clique is, it's like a block that's all filled in. Anybody know why the diagonal is missing here? What would the, Well, if there were dots on the diagonal, what would that mean? It'd be connections from a node to itself, right? Which, if we don't have those, it's called a simple graph. If we do have them, it's not a simple graph. Yeah, so we can see, if we have ordered things well, we can see these structures in a matrix. But if we don't, then we don't see any of this. Right? So here we have this big old clique, and we can't tell from this image because everything's scattered all over the place. There's a couple of trees. So this is the output of Grand Perspectives. This is a tree map of my hard drive. So here's all. This is Xcode over here. But you can see kind of from the outlines that there's this hierarchical thing. So Xcode is in applications. These are system library stuff. This is my home directory. This is Android images, stuff like that. So this is my virtual machine disk. But you can see this is like, there's, I don't know, probably 100,000 plus files in here. And I can totally navigate and understand what's going on here, right? Because we're using this implicit structure as opposed to, trying to connect everything with lines. So it's a great tool if you're running out of disk space. So some things that can help with seeing the structure is adding some shading information and also frames around this, so you can see. And you can also use different layouts. So that one was like a square rectangular layout. You can do radial stuff. I think I find the square stuff to be easier to read, but yeah. And here we'll look at if we're interested in attributes and topology at the same time. Here's an example of just trying to draw the attributes in a node link diagram with everything. Really hard to see. Right here we have like our nodes become histograms with error bars. Like that's again just so much noise. So this one is really cool. The idea here is we use the attributes to lay out the data. So we position the nodes based on the attributes. But they do it in a really clever way. So this is called graph dice. And so what you do is you pick two attributes at a time, and it lays out your data according to the attributes. And then when you switch, it imagines that the attributes are a face on like a cube, and it rotates the cube so you can see as it's rotating like where the third attribute is kind of related to the others. So this is a really clever thing. So you have all these different potential views, and I don't know exactly what they're doing there, but yeah, we can only really look at two attributes at a time in 2D, but this rotation metaphor I thought was really clever. When I click that, I think you'll. So it rotates into the new attribute. Yeah, so that was a pretty clever technique. Here's a tool for doing path extraction. So we have this node link view of the different nodes and paths. And once we select a path, then we can see the attributes that are associated with it. So to avoid showing the attributes for everything, we only show it for the things that are selected. So this is some sort of, I think this is a cancer data set. I don't understand anything about what's in it, but we're interested in some particular path, and there's these attributes that are associated with it. There's a couple more. These. So again, we have various paths, and we have the attributes that are associated with the paths. Tools you might look at. Gephi, I haven't played with this one. Cytoscape, I think, is for biological data. And NetworkX is what we're using. It's kind of a pretty simple Python graph data structure, but can handle a lot of what we do. Good. So, any questions about either the path search stuff or the graph visualization? All right. Again, hopefully everybody's gotten a jump on the next assignment. Started playing with the neural network stuff. Because it'll take a while to train stuff and experiment, so make sure you leave yourself plenty of time. And other than that, enjoy your weekend. I'll see you on Tuesday.